Hello, in this video we will review the notion of equivalence classes and prove some facts about them. So, given an equivalence relation on a set X, let A be an element of X. Then we define square brackets A to be the equivalence class of A. These are all the elements B that are related to A, so B is equivalent to A. As a first example, using the one we discussed previously, congruence modulo n. We say that two integers are congruent modulo n if and only if n divides their difference. So if you take an integer a, the equivalence class of a with respect to this equivalence relation is the set of all b that are related to a, which means b is equivalent to a, which means b is congruent to a mod n, which means n divides b minus a, which, if you apply the division algorithm and think about it, means that the equivalence class of A are all things of this form, nq plus A, where q is an integer. As another example from calculus, given two real-valued functions f and g, let's say that they're equivalent if and only if they have the same derivative. You can check that this is an equivalence relation, and the equivalence class of a function f would be those functions g whose derivative is equal to f. You can check that that means that the derivative of this difference must be equal to 0, right? Because by rules from calculus, that's just the difference of the derivatives, which is just saying that g prime is equal to f prime. But what does it mean for a function's derivative to be 0? Well, that means that that function is constant. So you're looking at all functions g such that the difference is constant. Well, that means you're looking at all functions of the form f of x plus c, where c is some constant. And so the equivalence class of f are all things of the form f of x plus c. And so you've actually seen equivalence classes in calculus. This is that infamous plus c when we do integration, that the antiderivative of a function is not a function, it's actually an equivalence class of functions. Any two of them differ by a constant. So now we get to a theorem about equivalence classes that may or may not be in the book, but it's one that turns out to be useful later when we talk about cosets and group theory. So suppose you have an equivalence relation on a set X. Consider two elements in X. Then the following four facts are equivalent. What that means is that once one of these four statements is true, all four of them are. And once one of these four statements is false, all four of them are. And so the first statement is just that A and B are equivalent. Well, if A and B are equivalent, then it turns out the equivalence class of A is a subset of the equivalence class of B. And actually, the equivalence classes are equal. So this is kind of interesting because it says the equivalence classes have to be, once you have containment, you actually have equality, which is kind of rare for sets in general. And then the last condition says that the equivalence classes, their intersection is non-empty. And so either if you're equivalent, then your equivalence classes have to have a non-trivial intersection. Well, I mean, in fact, the equivalence classes are actually the same. The more important part for 4 is that this tells you that if your two elements are not equivalent, then the negation of 4 is true, which says that the equivalence classes, so if A and B are not equivalent, then that tells you that the equivalence class of A and the equivalence class of B have empty intersection. And so they're completely disjoint. And so you start to see that any two equivalence classes have this feature. Either their intersection is completely empty or they're equal. Well, let's prove this result. One of the advantages of proving a theorem of the form the following are equivalent is that all you have to try to do is find some way to prove all the equivalences. So the approach we're going to take is this one. We're going to prove 1 implies 2, implies 3, implies 4, implies 1. So it's worth pointing out you don't have to prove 1 if and only if 2, 2 if and only if 3, and so on, because you can see from this diagram that, well, 4 implies 2 because 4 implies 1, which implies 2. So from any vertex on this graph, you can get to any other one by just following implication arrows. So you actually do see that any two of these statements must be simultaneously true. And this is always true for the following are equivalent statements. You just need some sequence of implications such that from any two statements you can get from one to the other by a directed path. If you have that feature, then you actually managed to finish the proof that the following are equivalent. And it's usually traditional for it to be something simple like a cycle, or occasionally you might get stuck with some annoying condition like that, where at least at some point you have to do an if and only if, which is kind of annoying. Anyhow, let's actually do the proof. 1 implies 2. What does that mean? That means we're assuming A is equivalent to B. What do we want to do? We want to show that the equivalence class of A is a subset of the equivalence class of B. How do you show a set? One set is a subset of another. Well, you take an arbitrary element of the set on the left-hand side, and you try to prove it's an element of the set on the right-hand side. So that's just what we'll do. We'll take something in the left-hand set, the equivalence class of A. What's the definition of the equivalence class of A? It's those elements that are equivalent to A. So by definition, X is equivalent to A. Well, let's look at our facts. We have X is equivalent to A, and A is equivalent to B. What do we want to get? We want to get X to be an element of B. Well, how do we get that? Well, we need to show that X is equivalent to B. Well, we see that since X is equivalent to A and A is equivalent to B, then we can use transitivity to show that X is equivalent to B. So we're able to solve this puzzle. So that's what we use here. Since X is equivalent to A and A is equivalent to B, by transitivity, X is equivalent to B. Thus, X is an element of B, so A is a subset of B, as we wanted to show. So this middle part comes from knowing where we want to go. This is where we want to go, and the only way to show this statement is to show this fact. And so these are the two facts we know. This is the fact we want to conclude. It's quite clear the only step we have left is to figure out how to do that, and there's only one way to do it, and that's to use transitivity. Alright, so 1 implies 2. Now let's try to prove 2 implies 3. So now we're assuming A is a subset of B. Or I should say the equivalence class of A is a subset of the equivalence class of B. And we want to prove that the equivalence classes are equal. Remember that two sets are equal if and only if the left set is a subset of the right subset and vice versa. Well, one of these facts is already given to us as a hypothesis. So all we need to do is show the other fact. We just need to show that the equivalence class of B is a subset of the equivalence class of A, only knowing one of the inclusions is true. So this is actually the trickiest part of the proof. So we make the attempt. Let's take an element in B. We want to, on the equivalence class of B, we want to show that it's in the equivalence class of A, which means we want to show it's related to A. Unfortunately, since it's in the equivalence class of B, the only thing we can conclude right now is that it's equivalent to B. Well, we know that the equivalence class of A is in the equivalence class of B, so we know that there is some element in here that is in here. In fact, I picked a particular one, although I didn't have to, namely A itself. Since A is equivalent to A is an element of this equivalence class. Since the equivalence class of A is a subset of the equivalence class of B, we have that A is an element of the equivalence class of B. Thus, A is equivalent to B. So all this work here was just to get this fact. Why do we want this fact? Because we want to prove that X is equivalent to A. And we know that X is equivalent to B. So we see that a good first step is to show that A is equivalent to B. And that's what we just did by taking advantage of this hypothesis. Unfortunately, to get from these two facts to this one, we see that B is on the wrong side to apply transitivity. But if you use symmetry, we can say B is equivalent to A. And now we have X is equivalent to B, B is equivalent to A. Applying transitivity to those two facts, we can cancel out the B and say X is equivalent to A. And that's what we wanted to show. Now we know X is in the equivalence class of A. So we start with an element in the equivalence class of B. We showed it's in the equivalence class of A. Thus, the equivalence class of B is a subset of the equivalence class of A. And we've now shown that these two equivalence classes are actually equal. Now we are on to the next step. This part is probably the strangest. What do we want to do? We're assuming that our two equivalence classes are equal, and we want to prove that they have a non-trivial intersection. Well, if they're equal, their intersection is just either equivalence class. So what does it mean for the intersection to be non-empty? Well, we just need to show that the equivalence class is non-empty. So we see by logic that we actually just need to prove something much simpler, namely that there's something in the equivalence class, which actually takes some thought. That's not obvious. For an arbitrary relation, if you define this notion of class, you're not necessarily going to get this. You need the relation to be at least reflexive. As we see, one way to prove that the equivalence class is non-empty is to point out that the equivalence class of A has A as an element, because A is related to itself. Therefore, the equivalence class of A intersect B is equal to the equivalence class of A, which is non-empty, because it at least has one element in it. Finally, to prove 4 implies 1, we assume that our two equivalence classes intersect non-trivially, and we want to show that A and B are actually related. And so we know that there's something in this intersection. There's some element X that's related to A and related to B, and somehow we need to get from that fact to showing that A is related to B. You'll notice this is similar to a proof we already did when we were showing 2 implies 3, and so it'll be the same idea. It looks like we need to apply symmetry to, say, this one, and then transitivity. So let X be an element in this intersection. Such an X exists because the intersection is non-empty. Then by definition of equivalence classes, X is equivalent to A and X is equivalent to B. By symmetry, X was equivalent to A, so A is equivalent to X. By transitivity, we have A is equivalent to X and X is equivalent to B. Combine those two facts in that order, and you see that A is equivalent to B. Putting those facts from that previous theorem together, we get another theorem about equivalence relations that is important for this course, which is that given an equivalence relation on a set X, the set of equivalence classes partitions the set X. And sometimes you define that notion of set partition in advance, but I'm going to define it in the statement of the theorem itself. That means the union of the sets in this collection. So a partition is a collection of subsets. So this union of subsets is the whole set. And the intersection of any two sets in your collection, in your partition, is the empty set. So in other words, the union of all the classes is the whole set, and the intersection of any two classes is either empty or the two classes are actually equal. 2, we essentially just proved, right? We already showed that if A intersect B is non-empty, then A is equal to B. So one of these two facts must be true. So we only need to show one. And one is not that hard. It's an equality of sets, though, so that's kind of annoying. But how do you do it? Well, clearly, equivalence class of A, by definition, is a subset of X. And since that's true for any A, the union is also a subset of X. That's a fact about unions that we often state. So we often state it this way in the proof writing course, but it's true for arbitrary unions. Why? Because if you take an element in this collection, it must be an element in one of the equivalence classes for at least one equivalence class. Since that equivalence class is a subset, that element is also an X. QED. Now we need to show X is a subset of this union. That means every element in our ground set X belongs to at least one equivalence class. Well, by reflexivity, everything is equivalent to themselves. So if I take an arbitrary element in my set, it's equivalent to itself. So it is an element of the equivalence class, its own equivalence class. Congratulations, that means it's an element in this union. So we have subset inclusion both directions, so we have equality. Therefore, the union of all the equivalence classes is the whole set, and we have this property. So to drive this proof home, suppose we work with congruence mod n. According to this theorem, every integer, the set of integers, is a union of these equivalence classes, of these congruence classes. However, as already noted, if you take the integer d, by the division algorithm, you can write it as a quotient and a remainder. Well, since Qn is a multiple of n, d and r are congruent mod n, which means they have the same equivalence class. And so this actually tells you that most of these equivalence classes are actually the same. So the distinct equivalence classes are 0, 1, up to n minus 1, the distinct remainders. And so actually you get a finite union. And so by the division algorithm, the equivalence classes of C mod for congruence modulo n are just these equivalence classes. And that's important to note because the way this partition looks, it looks like you get as many equivalence classes as there are elements in the set, and that's not actually true. There are infinitely many numbers, but in congruence mod n, there's actually only n congruence classes. It is worth pointing out that this example is very, very simple. In general, for arbitrary equivalence relations, we don't really get this nice feature where there's this nice, well-defined representative so that we can actually tell exactly which equivalence class a particular element belongs to. In general, that's a very hard problem.